Okay, welcome back. So in this video we're going to talk about the free body diagrams. So in a system, there's no system, natural or man-made, that consists of a single body in itself, but sometimes we can isolate a body in itself and showing the forces acting on it, on the system. So like the free body diagram, I can say free body diagram, what we do here, we draw a single body or a single system of body, single body or system of bodies. Here what we do to this, we show all forces acting on it, show all forces acting on this single body or system of bodies. Now, okay, so what do we mean here? Let's see an example. For instance, we have maybe, let's say, a book resting on the table. Okay, so simply, let's say we have a book like this one resting on the table over here. Okay, so this book is resting on the table. Its mass is m, it has a mass m. Okay, so the free body diagram of this book resting on this table, we isolate it from all the systems, so it's just the book. We even remove the table. Okay, let's say this is the center of the book. It's just this is the book. I'm letting it at that point. We can do whatever. So that's just like this point is just like the center of mass of the whole book. Okay, so which forces are acting on the book? Exactly, the first force is weight. It has its mass there, so the first force is weight. So what's the value of that weight? Weight, which equals to mass times g. Okay, now what's the other force acting on the book? Exactly, the other force is the normal reaction force. Now I want you to understand clearly here. If you've watched my video on Newton's third law of motion, I said in every action there is equal and opposite reaction. Now you see this force here, this weight is acting on this table, right? So there is an action, this is exerting a force on the table. But remember, if I place maybe this pen here, its weight will force it to go down, but it is not going down. It's just at rest there. Why is it not falling? Because this table or this paper is exerting the same upward force on this pen, which counterbalance and cancel, making it to be at rest like that one. No net force acting on the system, because if a net force could be acting, then the system could be in motion, could be accelerating. So because it's at rest, so the weight of this pen is counterbalanced by the normal reaction, because in every action there is equal and opposite reaction. So the normal reaction force, which is opposite, equal in magnitude but opposite in direction, so we have it here as n. So simply this is the free body diagram of that book. Let's see another example. Okay, we have that cylinder or that ball there, but my diagram is not good, which is resting on that groove here. It's resting on that thing. Now we want to show the free body diagram of that cylinder, of that ball there, that circle. So okay, let me draw aside the center of mass of that one and see the forces acting on it. So maybe this is the point here, the cylinder. I want to draw the free body diagram of this one. Okay, so this cylinder, I put it as down there, right? Now we have its weight, right? What is the value of its weight? Value of its weight, okay, exactly, the value of its weight is mass times gravity, which is mg, because have its weight acting down here. We are not given the mass, so no need to write mg. We are not given the mass equals to m. Now you see, this thing here is attached to this surface and attached to this surface here. So what does it mean? So that means there is a normal reaction force here between the cylinder and the two inclined planes, because this cylinder is attached, is in contact with this surface here. So if they're in contact, that means it's applying action force, which whereby this thing gives a reaction force. Okay, so we have a reaction force into this cylinder. It's acting on this direction, so I can draw it here, maybe somewhere, something like that, or I could have just drawn it here. It's all the same thing. The same ways goes to this one. So these are the forces that are acting on this ball here. Now you might ask yourself, why am I not including maybe this? Because this there is action force in every action. There is an equal and opposite reaction. In the former example here, we saw that there is a weight here down here and its reaction force up there. Now why don't we include the counter force, the action force, which maybe this ball exerts here? So we include maybe another force here, and then the ball acting, the force of this one acting on this one, we include it here. We do not include those forces there. Why don't we do that? Remember, we said the Newton law of motion, the action force and the reaction force acts on different bodies. This concept, you have to understand it carefully. They act on different bodies. If you punch a wall, and I'm repeating the Newton third law, if I hit this table with this pen, you can see. So if I hit it, this pen will exert a force on the table. Okay, so that force will be felt by the table. The action force will be acted upon to the table. If you see, so the table is the one that receives the action force. So if we were to draw the free body diagram of the table, we could say that the table experiences or is being acted upon by the action force. But remember, in every action there is equal and opposite reaction, meaning the table will also exert the same amount of force to the pen. Okay, so it will exert the same amount of force to the pen, the reaction force. That reaction force does not act on the table, but it acts on the pen. I'm repeating myself again. Action force, when I hit it, the action force will act on the table, but the reaction force will act onto the pen. That's why when I hit with a strong amount of force, the pen might be shattered away, might break, because of the reaction force that the table will exert on it. So these two forces act on different bodies. Action force will act on the table, and the reaction force will act on my pen. The same goes to this one. So this one, the force that this body is pushing in this slanted side here is acting on this side, so we do not include it. We want the free body diagram of this ball, but so we consider only the reaction force which this one exerts on this one, and the reaction force which this other side exerts on that one. Make sure you understand that one. It's very easy. But why did we include here in this first example? We included this action force. This is because this action force is weight, whereby this weight acts on the body. Am I clear? So because this action force of weight also acts on the body and acts on the system, because weight is the one acting on the body, causing it to go down, like how we included weight in this second example. Okay, hope that's clear. Now let's see another example here of free body diagrams. Are starting the basics, getting complex as we go on. Okay, we are given three blocks A, B, and C are placed one over the other as shown in this figure here. Now we are told to draw the free body diagrams of all the three blocks. So we want to show the forces acting on each of the three blocks. Okay, let's start with the first block, block A. Okay, so we have, let me draw this one, block A here. Let's say block A. block A, I draw maybe this is this one, so I draw a point here. This is block A, the center of mass maybe of block A, center of gravity. So we have its weight, the weight of A, right? So we have its weight. Weight always acts vertically downwards, perpendicularly downwards here. So this is its weight A. But remember, there is a normal reaction here. The normal reaction occurs when there is contact between these ones. So the normal reaction is perpendicular to that point of contact. Okay. So the normal reaction acts here. Yeah, I forgot to tell you this. Normal reaction is always perpendicular to the contact forces. That's why in this, from example here, the normal reaction was acting this direction here because it's perpendicular to these contact force points. See, the normal reaction was acting there. Okay. Now I think that's done for body A. Any other forces acting on it? No more. We are done with it. Let's see block B. Now, okay, block B might be a little bit more trickier. Okay, this is block B here. Let's start with the force that you all know it experiences. It experiences the weight B. Okay, this one is block B. It experiences the weight. But we have contact here and we have contact here. So there's normal reaction right here and there's normal reaction over here. Okay, let's start with this one because this weight acts here. So the normal reaction will act upwards. Okay, so that is normal reaction. So let me call this one normal reaction 1. So this one will be weight A and this will be the normal reaction 2. Okay, normal reaction 2 acts here. Now remember, I explained earlier about action and reaction forces. See this normal reaction of block A, it's acting here, the reaction. So this is because of the action force. So the action force of this block acts on this one, and it's the same amount of the reaction. Make sure you understood that. I told you, remember that example of me hitting the table with this pen. I said this pen will exert an action force to the table and the reaction will be exerted to the pen. So this reaction was exerted to block A, but its action was exerted towards the B. So we have another downward force here. Okay, we have another force here. Let me add it down here, which is N1. See, it's the same amount of as that force, but it is acting in the opposite direction because there's equal and opposite reaction. They act on different bodies. Okay, easy. Now we have again block, let's see block C. Let me draw it so as you can see the diagram here. Let me put it over here. Block C, this one. What are the forces acting on it? So this is the point here, the point. What forces acting on it? First we have the weight, it's weight C. So let me call this one weight C. Okay, and what about the reaction forces? Easy. This B here, we said it experiences a normal reaction from block C and 2. Why does it experience normal reaction from block C? Because it has exerted an action force towards it of the same value in 2 but different direction. So we have another force acting here down, so I just add it here. Okay, and that may, okay, but also remember there's a reaction force because it's in contact with this table. So there's another reaction force which is exerted by this table towards this one because this is exerting a force down here, the action force. So the reaction force, so let me call it N3. So that's the free body diagram of all the 3 blocks there. Very easy. Okay, let's see the last example here. Okay, this one, let's put an angle theta here. We are given a block of mass M is attached with 2 strings as shown in this figure. So we are told to draw the free body diagram of this block right here. So let me put the camera. They want the free body diagram of this block here. It's attached to this string and is attached to that string. So that means let's see the forces acting on it. Very easy. So let me draw it somewhere here, down here. So this is the block. Bring it as a point, that's the center of mass of that block. Okay, let's start with the obvious force. Of course, there is the weight mg, because they are told the mass of that block is m. Okay, here the block of mass m, so that means its weight equals to mass times g. Okay, now what other forces are acting on it? Imagine you are that force down right there. So there is this string here, there is this string here, and there's this string. So they're like tension forces pulling that body. Okay, yeah, we have this string pulling it upwards over there, we have that string pulling it upwards at an angle, at that angle there. So I can call this force tension T1 because they have other tensions here. And we have also this string pulling it to this direction here. Okay, it's pulling it towards that direction there. So I call that tension T2. Okay, now you might ask yourself, how did I know that the value of this tension goes towards this direction and this tension goes to this direction? Okay, there are a lot of ways of explaining this, but the way that I like to explain this is more imaginative, whereby I want you to maybe assume yourself you are here, you are this block holding on two strings. One is over here and the other one is over here. What will you feel? First of all, you will feel as if this string is the one trying to make you not to fall down, trying to push you towards this direction, right? It's pushing you towards this direction. So this body, this string is the one that is lifting it up, but in a slanted direction. Okay, it's not like pulling it down, it's pulling it up. See, if you feel it, if you can imagine properly. So this is the tension T1. But at the same time, if you were here in this rooftop, you could feel as if this string is the one that is pushing you to go downwards. So it's all about perspective, where you view things. Okay, so if you are here, this string you'll feel as if this string is pulling you upwards towards the roof, this one. But if you're here, you'll feel it pulling you downwards towards this mass here. So if you are taught to the free body diagram of this block here, you'll say this string is pulling this body upwards. That's why you say tension T1. The same as this one, this string is the one making it to be held on this direction, like it's the one pushing it towards the left. Okay, so that's why we put it tension T2. But if you were here, you could feel as if this block is the one pushing you towards this direction, the right direction. But because you're taught the free body diagram of the block, so we consider the block, how block feels these tensions are pulling it. So this block is feeling as if this string is pulling it towards this direction, and there is its mass. To find the values of T1, T2, that is explained in my other videos of resolving forces and other videos in this concept of forces. Make sure you subscribe to my channel. Thank you very much. See you in the next video.